All right, guys, today we're going to continue our discussion on the concept of equilibrium. We're going to focus more specifically on what's called Le Chatelier's principle. Those of you guys who had me last year, you maybe remember that. It says, how deep do you plant these and what kind of birds do they grow? Bird seed obviously grows birds. Okay, so you guys, so this continuation from last lesson, remember, so if we had this reversible reaction and you guys remember the process of ICE, I for initial, C for change, and E for equilibrium. Based on some initial concentrations, we can figure out what would be the concentrations once it's reached equilibrium. And then you guys remember using the equilibrium expression, you guys remember it's, what's equal to a constant is the ratio of products to reactants, and notice you raise it to a power equivalent to the molar coefficient. So when you take those equilibrium values, and remember at equilibrium those values are staying constant, because the rate going forward is the rate going in reverse, and so that tells you it's 51. So you guys know if it's a number greater than 1, what that tells you is as the products are favored, because obviously the products are in the numerator, and so if you have a number that's greater in the numerator than that in the denominator, you're going to get a number greater than 1. So the equilibrium constant does tell you something about a reversible reaction, even if you just had that value. Okay, we're going to introduce this other concept. So that was K. You guys remember as equilibrium constant. Q is very similar, but Q takes into account a situation that is at a time other than at equilibrium. Q gives the same ratio the equilibrium expression gives, but for a system that is not at equilibrium. So for example, if we were to calculate, let's say we plug in some values. We plug in some values according to the equilibrium expression. And if the value you get for Q is equal to K, what does that tell you? It tells you your system's at equilibrium, okay? But let's say you get a situation where Q is greater than K. Like for example, let's say we allow this reaction to go, and then at a certain point, let's say we're able to isolate all the reaction species, and we get these concentrations, okay? So then what would I do? I would plug those into the equilibrium expression, right? And just to make it shorter, let's say I plug those in, and this is what I get. Q is 200. What would I recognize? You guys remember what was K for that reversible reaction? Just going back, just so you guys can see. We got K is equal to 51. So at that particular temperature, so you guys remember, the only thing that affects the equilibrium constant, it's called the constant because it doesn't change, is the temperature. So it's 51, and so you see, based on these concentrations, I got a Q value that's 200. Notice, if this value is equal to 51, then I know, oh, my system has reached equilibrium. But we see it's greater. So what does that tell us? If I plug in values and I get a number that's greater than K, that tells you that, let's see, there's too much product and the equilibrium shifts to the left. Wouldn't you guys agree that if this number is greater than K, then that must mean, right, my numerator is much greater than my denominator would be at the point of equilibrium, right? Because I got a number greater. So what that tells me is my system is not at equilibrium. What that tells me is at this point, there's going to be a shift to the left. When we say a shift to the left, what we're saying is the rate of the reverse reaction at that point is going to be faster than the rate of the forward, and so ultimately you're going to end up producing more of that. Because when you guys agree there's going to be a shift to the left, decreasing the amount of products, which you guys remember is the numerator, and thus increasing the amount of the reactants, which is the denominator. And won't that cause if the numerator, that's the top number, goes down and the bottom number, the denominator, goes up? Wouldn't you guys agree that this value would go down? So this value would change. So obviously it's not at equilibrium. There's going to be a shift to the left until eventually your Q will equal your K. And then you guys can imagine, what if you take some values and you plug it in and you solve for the Q value, and your Q is less than the value of K. So you got a smaller number. Let's say you remember the K for this particular reaction is 51. Let's say we got 35. First of all, the fact that it doesn't equal K tells me it's not at equilibrium. And then what does that tell you? Well, wouldn't that mean that presently there's a shift to the right, that the forward reaction is faster than the reverse, because ultimately it's going to be shifting to the right, producing more products, increasing the numerator, and thus using up the reactants, decreasing the denominator, such that you get a point where your Q value will then become greater until the point that your Q is equal to your K. So if Q is less than K, that tells you there's too much reactant and not enough product. There's going to be shifting to the right in order to produce more product, and use up some of the reactant, ultimately until you reach equilibrium where your Q is equal to your K. Now we're getting to the big daddy, the Chatelier's principle. This was named after a French guy. And here's the basic principle. If a system is not at equilibrium, or I'm sorry, if it's at equilibrium, but then you disturb it, so now it's not at equilibrium. And you can do that by changing the temperature, pressure, or the concentration. What Le Chatelier's principle predicts, the system will shift its equilibrium position so to counteract the effect of the disturbance. It will always counteract whatever, so for example, if you increase the temperature, it's going to shift in such a way to ultimately lower the temperature. If you increase the pressure, it's going to shift in such a way to lower the pressure. So just to kind of help you guys see what we're talking about here.
Le Chatelier's principle states that if an external stress is applied to a system at equilibrium, the system adjusts in such a way that the stress is partially offset. The word stress means a change in concentration, pressure, volume, or temperature. Click on one of the buttons below to view animation showing the effect of these stresses on a system.
So let's see
at
if we
equilibrium.
change the concentration of one. So let's say there's a substance. Let's say, for example, you have this reaction at equilibrium. Then we go and end up changing the concentration. We pull out some hydrogen iodide, or we add some iodine, and we disrupt it. Once again, it's going to adjust and it's going to reestablish equilibrium. But then we're going to see how we can predict which way it will shift.
Iron-free thiocyanate, which is FeSCN3, dissolves readily in water to give a red solution. The red color is due to the presence of hydrated iron thiocyanate ions, FeSCN2+. The equilibrium between undissociated iron thiocyanate ions,
And just so you guys can see what's going on. So let's say we have a system at equilibrium. So we have three reaction species. And you guys can see it's kind of orange because it's got these red iron thiocyanate, the yellow iron ions, and then the clear thiocyanate. That's clear. That's showing you about how much it is. So at this point, you guys see if this is the reaction, when you guys agree, the left side, the reactant side of the reaction is favored, right? Because we have a greater concentration of that than that, okay? But you guys, right, all of the reaction species, and you guys see these at equilibrium, these are staying constant. So some of the red is breaking up into the white and the yellow, and some of the yellow and the white are combined together to form red. But it's not changing because the rate of the forward reaction is equal to the rate of the reverse reaction. So now we're going to disturb the equilibrium by adding sodium thiocyanate. Now you guys, you're like, where's sodium thiocyanate? But you guys see that that's an ionic compound. It's going to break up. You're going to have spectator ions. Sodium ions don't participate. But when you guys agree, you have these SEN thiocyanate. So by adding sodium thiocyanate, the effect is to add more thiocyanate ions. Look what happens. So we added more. So it's showing up here. I don't know if you guys can see that. So we added more of that. So now we have more whites, and I don't know if you guys can see here. But what's going to happen is now if you have more white, you're going to have more collisions between the iron and the thiocyanate, and thus what's going to happen is you're going to speed up the rate of the reverse reaction. And so then what happened is, so some of this gets used up, so there's ultimately a shift to the left, and you guys see what's happening? Whereas before it was orange, now all of a sudden the solution becomes pretty dark red. So by adding something to the product side, there's a shift to the other side, using up, guys, because when I added some, the thiocyanate was up here when I originally added, and so by shifting to the left, now it reduced it. Now obviously we still have, now it's at this point right here. Now obviously we still have more than what we had before because obviously we added more, but you see there was a shift in such a way that would minimize the disturbance. Okay, so hopefully you guys see that. So now, let's say we're starting, okay, we're at equilibrium, but now let's say we disturb the equilibrium by taking out some of the iron ions. So which way would you guys predict? Is it going to shift to the left and use up more of the iron ions, or is it going to shift to the right and replace some of the iron ions that were removed? Think about what Le Chatelier's principle says. He predicts it's going to shift in such a way to minimize or reduce the disturbance. So let's see if we add iron ions. So now we took away, so look, we took away iron ions, and so what's happening is, look, there's a shift to the right. And you guys see why that would be. Because now if we have less iron ions, when you guys agree, the collisions, the frequency of collisions between these two will be less. So therefore, what you've done is you've slowed down the reverse reaction. And so now, compared to the slower reverse reaction, isn't the forward reaction moving faster? So what's the effect? The iron thiocyanate is going to be breaking up much faster than these are combined together because there was less of it. So ultimately there's going to be a shift to the right, and in so doing, you see there was hardly any iron ions, but by shifting to the right now it's replacing some of the iron ions that were removed. So in this case, by removing some of the product, there's a shift to the right to replace some of the product. Okay, so that was changing concentration. Now let's see what the effect of changing pressure. Okay, so look, we have iodine, diatomic iodine, and then it can break up into iodine ions. You guys see and the ions, or I'm sorry, not ions, but the individual atoms. That's how much there is right there. I know you can't really see it. The reason why they have it there is because it's clear. But you guys can see at equilibrium, both of them are present. The diatomic I2 is present. It's purple, so that's why it's purple. You guys see there's a piston. So by moving the piston, we can change the pressure. Okay. So now I want you guys to make a prediction. Let's say we increase pressure. Okay. So we can do that by pushing down, because when you guys agree, now that same amount of gas is in a smaller confined area. Which way do you guys think it's going to shift? Remember, it's going to ultimately reestablish equilibrium, but which way will it shift? Will it shift to the right to produce more the individual iodine atoms, or shift to the left and produce more of the diatomic molecules? Let's see. So increase pressure. Increase pressure. Look what we're going to be doing. So we push it down, and now let's see which way it shifts. See, look at what happens to the color. It was pretty purple. And you know what I think? You're going to show it. Okay. We see ultimately there's a shift to the left, and it actually becomes more and more purple. Now you guys see, here's why you should be able to predict that. If we're going to increase pressure, Le Chatelier's principle predicts that the atoms are going to rearrange in such a way to minimize the pressure. It's not going to further increase pressure, minimize pressure. So then the question is, so you look at your two here, you look at what would result in lower pressure. Now look, you guys see the coefficient here. If the iodine atoms arrange themselves like this, I get one molecule. But if those same iodine atoms rearrange like this, you guys see I get two particles. So this is one, this is two. So the question I'd have is, what results in less pressure? More gas molecules or less gas molecules? When you guys agree less gas molecules, what's going to happen is the iodine atoms in a higher pressure environment are now going to collide more frequently, and thus you're going to have a shift to the left, resulting in these diatomic molecules. And you guys can see here, for every two of these, I only have one of these. There's a shift to the left, resulting in less overall gas molecules. If you guys were to count all these molecules, there's less than there were before, which is what Le Chatelier's principle would predict in response to an increase in pressure. So remember, you're going to predict it's going to shift in such a way to counteract the disturbance that was placed upon it. Okay. So let's do one that involves a change in temperature. Okay. So in this reaction, okay, so now I have colorless N2O4, and there's this much. And we see we have a brownish color NO2. And so you guys can see there's more NO2. So obviously in this reaction, the right side's favored. So if I were to calculate the K for this, wouldn't you guys agree it's going to have a K value larger than 1, right? Because I take my numerator divided by my denominator. Okay. So I'm going to tell you guys right off the bat, it's an endothermic reaction. So heat would be on the guys, right? You guys remember what endothermic means? Heat is absorbed. So when N2O4, when in the forward direction, N2O4 requires heat. When you have heat, what happens is the N2O4 molecules can break up into two NO2 molecules, and that's what this is showing. N2O4s, and then they're breaking up. But then in the reverse direction, when NO2 molecules come together, that's going to be an exothermic process because it forms N2O4, but not only does it produce NO2O4, it produces heat. So it depends on which way you're looking at it, right? Okay. So now what we're going to do is we're going to disturb the equilibrium. Okay, so it's at a nice equilibrium. These are staying constant. This is staying kind of a light brown. Okay, so let's increase the temperature. And you guys think, which way do you guys predict it's going to shift? Is it going to shift to the left? And you guys see by shifting to the left, it ends up producing more heat, or is it going to shift to the right and use up some of the heat? Well, if you increase temperature, let's see. Look at the color. heat that up. And you guys will notice, look, if this dropped here, you guys can see, look, this is getting much larger. So this dropped, and then this went up. We obviously, there was a shift to the right, and that's what you would predict, right? Because if we have more heat, you know what? You could look at it in this endothermic reaction. You could look at heat like a reactant. So if I'm adding heat, if I'm increasing the temperature, wouldn't I just be adding heat? And you guys know if you add something to the reactant side, there's going to be a shift to the product side. And you guys can see kind of why. Because if we got more heat, if heat is required for N2O4 to break down to NO2, if I got more heat, when you guys agree that that process will be occurring much quicker, so the forward reaction will be faster, right? And you guys see this is what it's initially happening. The forward reaction is now faster than, remember initially at equilibrium they're both the same rate, but now all of a sudden now the rate of the forward reaction is faster than the rate of the reverse. There's the shift to the right and you end up producing more NO2, which is the brown color. You can see it became more brown. And then ultimately, once again, it's going to reestablish equilibrium, right? But initially there's going to be a shift to the right and ultimately it's going to turn more brown. And you guys can kind of see this. You know, that's essentially how mood rings, you guys know mood rings, that's how they work. It's just using an equilibrium system, and you guys can imagine what's changing the color of a mood ring isn't it the temperature in your body. So they're using a reversible reaction materials in the mood ring that's just going to change, shifting either way depending on if you're adding heat or removing heat. Okay guys, almost done here. This is very, very important, is the Haber process or the Haber process. You guys, this was revolutionary. This changed the world. Basically, the Haber process is a process that was used to ultimately produce, it was an efficient way to produce ammonia. Ammonia, you guys remember ammonia is NH3. And the key thing about ammonia, it's not just that you could produce more Windex. Ammonia is a key ingredient in fertilizer. So basically they were able to come up with an optimum way to produce ammonia, which is a key ingredient in fertilizers. And you guys can imagine, how does that change the world? Well, fertilizer are used to grow crops, and so now you can solve a lot of the world's lack of food crisis with improved fertilizers. So where do we get ammonia from, NH3? We get it from nitrogen and hydrogen. So nitrogen and hydrogen diatomic molecules will combine to form ammonia. So let's just show what that looks like. So we'll have N2 plus H2, and that is a reversible reaction too, assuming, right, it's in a closed system. It's a closed system. Okay, so then, right, we have to balance it. So I think we're going to go to here. Yeah, there we go. Okay, so that's our reversible reaction. So what I want us to be doing is thinking, what can be done to the system to maximize the production of ammonia? What do you guys just think, right? Let's just, obviously we have to have a closed system, otherwise we wouldn't have this reversible reaction, so we want to have a closed system. And so obviously, what do you need if you're going to produce ammonia, obviously what do you have to put into your reaction vessel? Don't you have to put nitrogen in there? And don't you have to put hydrogen in there, right? You put that in there, and then some will, so if we want to maximize the production of ammonia, what are we trying to do in light of the concept that we've just been talking about? Which way do we want the equilibrium to shift? Right, so what I'm asking you is what kinds of conditions, what can we do to get it to shift to the right, right? Because there's going to be a certain amount of ammonia produced, but then at equilibrium, it's just going to stay the same concentration of ammonia. We want to constantly produce ammonia. So I'm hoping you guys at this point, you guys are stopping, you guys are thinking, what could I do? I'm thinking right off the bat, what do you guys think you could do? If you want to get more ammonia, what are you going to do? When you just add more reactants, right? So let's say we add hydrogen to the system. So you guys look, so at equilibrium, all of these concentrations are staying constant, right? Because the rate of the forward is equal to the rate of the reverse. So these are all staying constant. Now all of a sudden we disturb the equilibrium by adding more hydrogen. Okay, so now I have a lot more hydrogen I put in there, and you guys can see what's the result. Now if I have more hydrogen, when you guys agree the frequency of collisions is going to be much more between the hydrogen and nitrogen, thus speeding up the rate of the forward reaction, and then what's the result? You're going to end up producing more ammonia. And then obviously what's the result on the amount of nitrogen? Isn't the amount of nitrogen going to slowly, it's going to decline, right? Because we're using up some of the nitrogen combining with the hydrogen. So obviously you guys, we can add more nitrogen and hydrogen. That's one way. But now you guys think pressure and temperature. Oh, and you guys know this is it's an exothermic reaction. So it's an exothermic reaction. What do you guys think? What will we do at temperature? Imagine you're a chemist working for Dow Chemical Company. You guys are making fertilizers. You want to maximize the production of ammonia. How could you do that? What kind of environment would you guys keep this in? Would you guys have it cranked up to extremely high temperatures, or would you have it at low temperatures? Hopefully you guys agree you would put it at a lower temperature. You guys see why? What does Le Chatelier's predict? If you put it at a lower temperature, it's going to shift in such a way to try to, remember, counteract, increase the temperature. Well, you guys look, as you go right, not only are you producing ammonia, you're producing heat. So by lowering the temperature, we would expect a shift to the right, and what we mean by that is, right, when we say shift to the right, basically we're saying that now the rate of the forward reaction is faster. Because when you guys agree, look, you guys see why, look, lowering the temperature, isn't it kind of like you're removing heat? Well, and you guys look, if you're removing heat, for ammonia to produce nitrogen, to break up into nitrogen hydrogen, it needs heat. So going this way, it requires heat. Well, if I have less heat, when you guys agree that the rate in which the ammonia breaks up into nitrogen and hydrogen slows down, and so at that point, whereas before they were equal, now at that point, since the rate of the reverse slows down, the rate of the forward is faster than the rate of the reverse, and what's the ultimate result? You end up producing more ammonia. Okay, last thing we can do, you guys remember, we can change the pressure. Would I want to have this reaction happen under a high pressure situation or a low pressure situation? Kind of look what's going on. When you guys agree, you'd want it at a high pressure. Because you guys think about it, under high pressure, Le Chatelier's principle predicts it's going to shift in such a way to lower the pressure, always reduce. And you guys, what arrangement of atoms results in lower pressure? More gas molecules or less gas molecules? When you guys agree, less gas molecules. So then I just compare. If all the nitrogen and hydrogen arrange themselves like this, how many gas molecules do I get? 1 and 3. You guys look at the coefficient, I get a total of 4. But if those same atoms arrange themselves like this, how many gas molecules result? Only 2. So what's the result? There's going to be a shift to the right, producing more ammonia, but you guys see overall less gas molecules, which lowers the pressure, which is what Le Chatelier principle would predict as a response to the increase in pressure. So that's what Haber kind of figured out. He figured out, hey, so guys, check it out. Look at what we've got here. This is really the Haber process. Check out how this is. It's kind of sophisticated. So obviously you got to put in nitrogen and hydrogen, so you're constantly putting that into the system. Now you guys notice, look, it has a heating coil. But some people are like, wait a minute, Mr. Wilson, didn't we say lower temperature? Yeah, but you still have to heat it up. But you don't want to have it at excessively high temperatures, right? But then some of you guys are going to be thinking, what's the problem with having a chemical reaction happen at lower temperatures? Aren't reactions that happen at low temperatures happen what? Very slowly, right? And it's too slow. So that would be inefficient, right? You don't want to have just a super slow process. So maybe you guys can look at the diagram. So we want to have it at relatively low temperatures. Now you guys are like, man, that seems pretty high, 460 degrees Fahrenheit. But compared to like 1,000 or 10,000 degrees Celsius, that's relatively low. But you guys see, what could you use to help counteract that slower reaction speed due to lower temperature? Use a catalyst. So obviously they figured out a catalyst, right? And a catalyst that was specific to this reaction, and you guys remember how a catalyst works, it changes the mechanism, and most likely what happens is it allows the nitrogen and hydrogen to bind to the catalyst in such a way that when the nitrogen and hydrogen come together, they're going to come together in a more efficient way with the proper orientation, and thus it's going to speed up the reaction between those. So we use a catalyst at a lower temperature, okay, and so now you can imagine, so ammonia gas is being produced, okay, so ammonia, and then you also have the unreacted nitrogen and hydrogen. Then what we're doing is we're using a pump to compress the gases. What do we say we wanted? Higher pressure, right? So we're going to compress the gases, basically take all that, you guys see it's in a bigger volume, and then you compress it by putting it into a smaller space. Then what happens is, you know, as you compress it, right, once again, there's a shift to the right. You're producing ammonia. Now here, get this, guys. Oh, there's one other thing that we didn't talk about. Now what you do is you put it at a very low temperature. And if you guys look, and some of you guys could even predict which would have higher, stronger intermolecular forces, nitrogen and hydrogen molecules or ammonia. When you guys agree, ammonia molecules, remember this is a polar. So this has stronger intermolecular forces, therefore it's going to have a lower boiling point, which means it's going to go from a gas to a liquid at a much lower temperature. So they're going to bring a temperature down, and what do you guys see begins to happen to ammonia? The gaseous ammonia now condenses into a liquid. And so essentially what else did they do? Not only do we add this, when you guys agree, if you take out ammonia, when you guys agree, if I remove ammonia, wouldn't there be a shift to the right, replacing some of the ammonia that was lost? So by condensing it at a certain temperature, so they bring it to a temperature at which the ammonia liquefies, condenses back into a liquid, yet the nitrogen and hydrogen are still present as a gas, and then the nitrogen and hydrogen are just recirculated to the process, and it goes over and over, and that maximizes the ammonia production. All right, guys, that's kind of what chemists do, right? You kind of have an understanding of basic concepts, understanding of how the matter interacts, and then we design, experiments, and we design, in this case, a process that's going to maximize the production of a reaction species that we desire. All right, guys, that's it for equilibrium. Until next time.